So good morning everyone. Today we are here to discuss about our fourth module on classical mechanics. It's about nonlinear equations and chaos. And as you know, in last few classes we were discussing about small oscillations and before that we have discussed about a rigid body dynamic system and all. Okay? So even you may be remembering in that in the last class when we are discussing about the triatomic linear molecules discussion, so where we are interested in the small oscillation corresponding of a triatomic molecule, that too a linear triatomic molecule that we were discussing in that session. Okay, so we basically need to say that we are interesting only on the simple harmonic motion in that case. Okay, so in last class when we are discussing about a small harmonic motion corresponding to a molecule, so our interest was only on based on to address the linear change corresponding to that molecule's discussion. So that's why we are taken only a simple harmonic motion in that case, right? So we just treated as a harmonic oscillator which is having a simple harmonic motion, right? So we are interesting about the simple harmonic motion. And what we are, when you consider the force in that case, so which has a restoring force in that case, so that's what the restoring force was proportional to x in that case. Okay, so when you consider a simple harmonic motion, so generally we treated that there is a restoring force which is proportional to x in that case. And also we can say that it doesn't depends on x square and s cube. So what mainly we are dealing in this module is that, so we'll be discussing about the nonlinear systems. So there we cannot say that always the system is in linear. What linear means? Simply we can say that linear means if you take that P is proportional to E. So where P is the polarization and E is the electric field, you just see that. And if it is proportional to E means what? So when you plot a graph like that, so you will be having a linear dependency over there. That when you increase the electric field over on a particular direction, you will be corresponding, the polarization is actually along the increasing with respect to electric field. So P proportional to E means what? So the dependency on polarization on electric field is linear in terms of that. Okay, that is more important in the case of a linear system. So whenever you address a linear system, so the system dependency on the parameters on the system will be linearly dependent with the other deciding variables in that case. So here the variable is electric field, and corresponding to the electric field there will be a polarization change. Okay, so in a simple harmonic motion also, when you consider the restoring force which is actually proportional to the x, where x is the displacement or the change in position. Okay, so it is restoring force is proportional to x. So normally there are two type of system, basically you can say that one is a linear system, another one is a non-linear system. So as you know, for a non-linear system it is difficult to define the property of a non-linear system, because we cannot say that it is exactly depend on a particular parameter. So it will be also we cannot say that it is not a predictable case also. So most of the non-linear system is a unpredictability is also always there. Okay, so the oscillation will be unpredictable. For example, uh, if simply if you take a particle in a box and you start vibrate the box, and you start for, you just kept a number of particles or a balls inside a box, and you start vibrating that uh, box, and we cannot correctly exactly say that the all the balls will be vibrating in the same frequency or same motion, so it will be executing same displacement. So it sometimes, when you consider the entire set of particles, we cannot actually define that it is directly proportional to something, that is it is linearly dependent to another one. So there are two type of system basically we can address. One is a linear system, another one is a non-linear system. Okay, so when you discuss about a non-linear system, as we know, when we consider a linear system, that is a line equation, right? Line equation, if you represent, we represent as y is equal to mx plus c. Okay, where m we represent as a slope and c we represent as the intercept corresponding to that. For this case, we know that the intercept will be 0 in this case. Okay, and if there is another graph I plot with respect to y, okay, this is my y, this is my x, then we represent the linear dependency is that, and if you take the slope of this graph, slope is what? It is m. Okay, and the intercept means what? This is c. So this is the intercept corresponding to that. In this case, the intercept will be 0. Okay, so basically for a linear dependency, we have to represent the equation in terms of mx plus c. Okay, at least we have to get it as a linearly dependent over there. Rather, we can represent in other ways also the linear dependent equation, but simply if you just represent a line equation, that will be take the form y is equal to mx plus c, and corresponding to that you can easily find a slope corresponding to that and an intercept corresponding to that line. Okay, and the dependency, mainly the dependency in terms of, I have to say, so y should be proportional to x. Okay, so that's what we also see in simple harmonic motion. So the importance of understanding this nonlinear equation and the chaos module is that we know that in our earth, all the phenomena what we observe, all the phenomena we observe in our surrounding, is not always linear. Most of the phenomena we it's observed will be non-linear in case. So there are two type of non-linearity can be addressed, which is with respect to one, what I can say is that it's about the way parameters it is moving. For example, if it is in this simple harmonic motion, the main parameter dependency is what? It is on the displacement of the particle from one point to another point. So there is a non-linear variation of the particle with respect to, when you considering the force, the change in motion with respect to x, if you consider, so that is the one we will be depending on that. If it is that is in non-linear, we can say that the system is non-linear. Otherwise, there are another way of representation as well, which is representing in terms of time. Okay, if there is a time is a non-linear in case, that system also we can call it as a non-linear system. We say that the time is moving like 1 2 3, it's moving like that. And there are some other cases the time will be varying non-linearly. Okay, in that case also we have a non-linear system. Okay, anyway, just I will be giving the brief introduction to that. Now we'll examine what our non-linear equation is, that how do we address a non-linear system, how do we represent that, and how we solve a non-linear equation. Okay, that will be our discussion for today. So today I will be giving not in very detail, but I will give the brief introduction to the module, and we'll go further with few more modules. So hope you will not be very familiar with the chaos, but you may be heard of different condition. So this is a very chaotic situation, like the word you have seen. Chaotic means it was difficult to we can difficult to give a proper decision, or like one of the classic example of a chaotic system is that it is about clouds. Okay, the atmospheric clouds is a classic example of a chaotic system, because we cannot actually define what is the shape of a cloud. So the cloud can be in a different shape. There is not a proper shape according to the for a particular cloud. So chaos, the classic example of a chaos system is our atmospheric cloud itself, because it doesn't have a proper shape, proper defined property. We cannot define by linearly, we cannot define the property. Okay, so first we will address the nonlinear equation. What are nonlinear equation, how do we generate and how do we solve a nonlinear equation, Then we'll move on to the discussion of a chaos system. Okay, let me come back to our first example, a simple harmonic motion, where we have a restoring force which is actually proportional to what? It is proportional to x. And we can say that it does not depends on what? The dependency is, that does not depends on x square or x cube representation. Now, if you represent a differential equation corresponding to this, okay, so therefore a differential equation, when we represent corresponding to this restoring force, we have to represent that this is a differential equation corresponding to force proportional to x. So we'll have a terms what we have, x will be the, and dx by dt will be the, because we are evaluating with respect to the rate of change of uh, motion, okay, displacement. Or then the second order, if you take d square x by dt square x. So where we are evaluating with respect to time the change in motion with respect to, or change in displacement with respect to time. Okay. So when you, hope you know that when you evaluating dx by dt means what? It is where we are evaluating very small displacement. So when you consider a box like this, when you take a dx by dt, what you are actually evaluating? You are evaluating an area, or rather it is a small area, very small cross-sectional area, we just represented by a dx by dt. Okay, so this is basically what? There are two dimension, x is there on the dimension, and the another one is time. So with respect to x and time, you are actually evaluating this area, and what we are getting is that, so when you do a differentiation, what you are basically doing is you are evaluating a very small area, so behavior of a very small area, and what you are getting mathematically is that a very small area representation. Hope you remember that when you do a integration, what you are actually getting, so you are actually getting an area, a property of an entire area you are getting while you are integrating these all terms. So dx by dt plus dx1 by dt plus dx2 by dt plus, so you are actually doing x1 plus x2 plus x3 like that. So the mathematical representation of dx by dt is what? It is a smaller area, so when you do integration, so you are covering the larger area portion. So that is a physical significance of a integration and a differentiation. So okay, so now what I do represent here is that what is dx by dt means. Physically what it means is that if there is a change in position with respect to a change in time, okay, over a small volume, if this is a t1 and this is a t2, and correspondingly there will be a change from x1 to x2. So that is basically you are evaluating from, if you are taking a differential equation. Okay, so when you consider a simple harmonic motion here, so we have a restoring force which is proportional to x, right? So we have seen that when you consider a differential equation with respect to time, then you'll have first term will be x dx by dt, then d square x by dt square. Okay. Now what we can say from this differential equation is that this differential equation is said to be linear. Okay, this is said to be linear in x and its derivative. Sorry, and its derivative. So now we know when you consider a harmonic oscillator, how do I say it's a linear dependency? So because we know that, so for example, for a harmonic oscillator, we do represent that the corresponding equation of motion will be like this: d square x by dt square plus omega 0 x equal to 0. So this is the case for a harmonic oscillator equation of motion representation. Okay, so this is a linear equation. You can see that this d square x by dt square is varying with respect to uh, the change in x with respect to time plus omega 0 square x. So this is a linear equation of representation. Now let me show you how a nonlinear equation representation corresponding to a harmonic oscillator will look like. For a nonlinear case, when you represent, so this will be slightly like this, okay? D square x by dt square plus 2b dx by dt plus omega square x equal to 0, and hope you remember that this equation is correspond to a damped harmonic oscillator, okay, a damped harmonic oscillator representation. So if you remember, this is an equation corresponding to an harmonic oscillator, d square x by dt square plus omega 0 square x is equal to 0. And if there is a damping corresponding to that, d square x by dt square plus 2b dx by dt plus omega 0 square x is equal to 0, which is a damped harmonic oscillator. So hope you remember that for a damped harmonic oscillator, the dependency will be like how the waveform corresponding to that, the waveform corresponding to that will have a representation which will be slightly like this, okay. If there is no damping, so we can say that it will be actually like a, the amplitude will be same over the time. So if you just represent x or t with respect to that, normally the solution will be in terms of x is equal to a cos omega t or a sin omega t. So if the amplitudes will be constant throughout the time, but there is a change in displacement that you can observe for a linear case. For a damping case, we cannot say that all the amplitudes will be same. So it will be varying and it is getting smaller and smaller, and it will be coming close to 0 as time goes. Okay, so a damped oscillator, which is an example corresponding to what, it is a nonlinear system, we can say that, okay. And whereas in this case, uh, for harmonic oscillator we can treat this as a linear system. And what the exact change here is that it is 2b dx by dt, where b is actually contributes as a nonlinearity. 2b is contributing to the nonlinearity to this equation, okay. Now if you say that, now let me say that, let f1 x1, sorry, f1 xt and f2 x of t are the two linear solutions, okay, two linear dependent solution for any linear system, okay. Then we can also say that the corresponding c f1 xt and c2 f2 xt also a solution corresponding to a linear system, okay. It's also a solution corresponding to the, if there is a linear system, if you are a linear system and it have a linear dependent solution, that is f1 xt and f2 xt are the two linear dependent solution for a linear system, then we can also consider that c1 c2 are the two constant, c1 into f1 x of t and c2 f2 x of t is a also solution corresponding to a that linear system of case. Now if you consider, we have seen that there is a case, according to, we have seen a case, in this case there is a linear system we had, and we have a non-linear system we have seen here. Now if you define a non-linear system, as I said, the non-linearity can be in two ways, okay. Non-linearity can be in two ways, that is, one is depends upon the variable, For example, as I said, if you just define y is equal to mx plus c, and if the nonlinearity in terms of x is means what? It is a change in position, right? So if there is a change in nonlinear change in position, okay, nonlinear change in position, then there will be with respect to time, with respect to a proper time t, then we can call this as system as a nonlinear system, okay. And similarly, if there is a corresponding time is varying nonlinear, if you see any case time is varying nonlinear, and in that case also we can call a system nonlinear system, okay. So basically what I want to say is that a system whose time evolution equation, if the system's time equations are nonlinear, which are called a system whose time evolution equations are nonlinear, then we call it as nonlinear system, okay. Now what is the case of a nonlinearity case? Now you can see that in a damped case, damped harmonic oscillator is that, so here we have a time evolution equation, that is d square x by dt square dx by dt plus omega square x. So this is actually representing a time evolution equation, that is a change in time with respect to time. What is x means? X means normally we do represent that at x is equal to t equal to 0, and at dx by dt means what? Is the time changed from t0 to t1. And when you consider d2 d square dt square, what it means is that it is again t1 to t2. There is a change, second order change corresponding to that, okay. So there is a time evolution actually is happening. Actually what is changing over there is that the time is changing with respect to that you are evaluating the x, okay. So change in time with respect to x is we are basically evaluating there. So any system whose time evolution equations are nonlinear, that it means, so when you examine change in x with respect to t, so there if there is a nonlinearity in that representation, then we can call that is a nonlinear system, okay. And what is the important property that is we can say that about uh, nonlinear system is that it does not follow principle of superposition, okay. A nonlinear system, a nonlinear system does not follow or obey principle of superposition. Hope you remember what is principle of superposition is that. Simple example I would like to say that when you consider electric field, so electric field due to a number of charges, okay, then if you want to get the total electric field, so you want to examine that it is E equal to E1 plus E2 plus E3 plus etc like that. That means, so if you want to find the total electric field, it will be a summation of the each electric field given by each charge q1 q2 and q3. So if it is only we can say that the dependency is linear, in that case we can apply this principle of superposition. So the greatest benefit of a principle of superposition is that, so if you want to get the entire electric field of a number of charges, which we can say that it is a summation of the electric field due to each charges. But when you consider a nonlinear system, we cannot actually define that. We cannot actually say that, or we cannot apply the principle of superposition because it is non-linearly varying. Here E1 will be different, E2 will be different, and E3 will be different, and dependency on E. For example, now if I just represent this in terms of time, so here E will be equal to E1 of t will be same, and E2 of t and E3 of t with respect to time, all varying will be linearly with the time. If that is a condition, then we can actually apply the principle of superposition. But when you consider nonlinear system, the dependency of electric field on time, for first case maybe it is maybe behaving like linearly, but in the second case the electric field due to the charge q2 will be in non-linear. So in that time we cannot actually represent this is in terms of like that. It will be, the dependency will be t minus t0 or something like that. Okay, so in such cases, so we cannot say that the nonlinear system cannot be applied to or cannot be used using principle of superposition. So what we generally say that nonlinear system does not obey or follow principle of superposition. And before coming to the example of a pendulum, let me give you a brief idea of a nonlinear system as well. So generally, when do we represent about a conductor, we know that when you increase the current, the voltage will be increasing in linear with respect to that. Okay, this you represent as vi characteristics of any sample, or rather if you just simply you'll be getting, so for a conductor if you do so, this is you'll be getting your resistance, then that too you represent as v is equal to ir, right? V is equal to IR. So that is V is proportional to current. So when you increase current, the voltage is also increasing. So there is a constant representing, that is R, which we call as resistance. And similarly, so this is the case for a conductor or a resistor, simply we can say that. And what do we the case for semiconductor? How do that representation? A simple example of a nonlinear system I could say is that, so hope you remember that for a PN junction diode and all, so the graph will be almost like this. Okay, okay, it will be coming through the zero origin only. By the dependency will be almost like this. So here we cannot exactly say that. What is we call this as? This we used to call as Ohm's law. So Ohm's law is actually the linear dependency on voltage with respect to current. How do we represent in this case? Is that linear like a conductor? No. For semiconductor, there is a portion we do say that it is nonlinear dependency over there. Okay. So there will be a small region that is having linear dependency, but there is also some region where current and voltage is nonlinear in case. So here we cannot say that Ohm's law is not obeyed in this case. Okay. So with that itself we'll be able to understand is that what is a linear system. It's an example. And uh, when you go through in detail, there is always a branch which is called, as you know, there is a linear optics and non-linear optics is there, and similarly there is a non-linear electronics part as well. There are few phenomena like semiconductor, insulator. With when you discuss about that, that too is a linear non-linear systems. Okay, so non-linear optics, you know, and when you consider non-linear, okay, non-linear electronics is there, non-linear optics is there. So these all are finding a lot of applications in a different manner. Okay, so for that, those all discussion, this will be an introductory part for those all nonlinear system and equation. Okay, so I just given an example of conductor semiconductor example where you can actually correlate what is a linear and a nonlinear system will almost look like. Okay, so I'm coming back to our classical mechanics discussion. So our discussion always will be moving on to based on a harmonic oscillator and a pendulum case. So let me take an example of pendulum. Okay, Hope you would have already done many discussion of pendulum in your first two module. So let me just take the same information back here. Pendulum. Okay. So in pendulum, we have a general equation corresponding to a pendulum. Equation of motion is what? It is d square theta by dt square. Right? So we do represent that there's a pendulum, it's moving, which is actually oscillating from its original position to another position, and which we can do represent that this is theta and this is L sine theta and this is our L. Okay, this representation you would have already done in your classes. So let me take the equation of motion corresponding to a pendulum. So d square theta is equal to what? It is minus gl by sine theta, or rather you can simply explain as like this: d square d theta by dt square plus g by l sine theta equal to 0. Okay, you can either represent like this. Now if you take, if theta is very small, okay, okay, compared to sine theta, or rather I can say that theta is very small, theta is very small, in that case we can say that this equation will be how it look like. Is we can simply represent that if theta is very small, this will be a linear equation because there will be no dependency on sine theta. So we can say that d square by theta dt square will be just g by l, okay, equal to 0. Okay, or rather d square by d theta by dt square equal to g by l. This is because theta is very small, then sine theta we can just neglect, then we'll be getting only this, and this system will be, in this case, if theta is very small, this system we can treat it as a linear system. Okay, if theta is very small means what? It is associated with the small oscillations, right? So the oscillation will be very small, the change in displacement will be very small. Then if the change in displacement is very small means we can just treat this system as a linear system. The change will be linearly varying. Now if we have to say that the condition is that when the theta is comparably large, okay, let me say that theta is comparably large. If the theta is comparably large, then you have to take that sine theta, you have to take into consideration. Okay, so you have to consider sine theta itself. Okay, so what is sine theta? Sine theta, if simply if we expand by expansion, so then this we can represent as theta minus theta q by 3 factorial plus theta raised to 5 by 5 factorial. Like that you can expand this corresponding representation. Now if you introduce that into the equation, how do it will change? D square theta by dt square plus g by l into theta minus theta q by 3 factorial plus theta raised to 5 by 5 factorial, like it will goes on, so which is equal to 0. And now you can see that there is a dependency on theta cube and theta raised to 5 over here. Okay, now this equation becomes what? Now the equation becomes when there is a when the theta is comparably larger, this will becomes what? It will become a nonlinear system. So how do we simply examine is that if you just moving a pendulum with a very small oscillation, we can just define the motion as a linear, because we can easily can say that it is moving very slowly and the motion is almost like linear. So when you keep it in a very large amplitude or rather large displacement and keep on hanging, and you can itself observe is that the motion will be non-linear in motion. and the change in theta, when you look into the basic picture of that, in that case the change in theta will be larger for larger values of theta, and you have to accommodate sine theta there, where sine theta is what? It is theta minus theta cube 3 by factorial. And what is the case of this? Because here when you examine this small equation, let me say that this equation has a dependency of theta here. Okay, it is varying with respect to theta, and here also theta, but here you can see that it is varying also in terms of theta cube. Okay, it is varying in terms of theta cube, and it is varying in terms of theta raised to 5. Okay, if simply g by l theta is only there means, then you can say that it is simply a linear equation. For example, let me say that d square theta by dt square plus g by l theta. Okay, if it is simply like this means, you just examine, this is a linear equation, or this is a linear system. But what about the other case? So if not the other case, d square dt square plus g by l into theta minus g by l theta cube raised to 3 by factorial plus g by l theta raised to 5 by factorial. So it has dependency on theta cube and theta raised to 5, like it goes on. So this system is a non-linear system, and this is a linear system. So this is a simple case for a simple pendulum, where there are two cases is considered. One is a linear case, another one is that a non-linear case of discussion. Similarly, when you represent a equation like this, similarly if you consider a harmonic oscillator, in the similar case we'll do have d square x by dt square, okay, plus omega 0 square x is equal to, for example, alpha x square plus beta x cube and plus alpha x raised to 4, like this. So here you can see that there is a change with respect to x, x square, x cube and x raised to 4. So when you have to consider x square dependency, x cube dependency and x raised to 4, okay, then this will become a example of a nonlinear equation. Similarly, another example of a nonlinear equation is that we have d square x by dt square, okay, minus, let me take epsilon into 1 minus x square dx by dt plus x is equal to 0. Okay, in this case also you can see that there is an x square term in addition to the x term over here. So this equation also becomes what? This equation becomes of a nonlinear equation. Okay, these two are a nonlinear differential equation in that case. So these are the representation of a nonlinear equation, where we have a dependency on x and x square or x cube or x raised to 4, simply is to verify a nonlinear differential or a nonlinear equation. Okay, clear? So what we have done is that there are two cases we can basically address. We have taken the example of a pendulum, and in the case of a pendulum there will be two chances for a linear and a non-linear system with respect to the change in theta. Okay, so similar extension we can also extend it to a generalized representation corresponding to that. Now in this case what we have basically done, so if a nonlinear differential equation does not contain an independent t, okay, independent time t. In this case, if you just check down, you can see that here there is a dependency on time, but there is no dependency on time for x square and x cube and x raised to 4 changes. In that case, if a nonlinear differential equation does not contain a independent time, so it is a fair difficult so to obtain the proper property of the system. So we need to know that we should find a independent t in order to find a fair amount of knowledge about a system to be found out. Okay, so for a dynamical system we know that we will consider a dynamical system. What is a dynamical system and what is a statical system means? We know that electrostatistics and electrodynamics. Static means with that there is no change in time. Okay, so we'll only interested about the uh, when the time equal to t equal to 0 or time equal to t equal to 0 only. Okay, when there is a change in time, then we'll be consider about the dynamics of that one. Okay, if there is a change in time, then we have to discuss the dynamics corresponding to that, that is dx by dt or something that's t equal to t1 t2, like it is varying in a dynamic system. So as the time moves, the change corresponding to the position or any property of the sample, such system we used to call as a dynamic system. Okay, anything that is moving with respect to any parameter that is changing with respect to time, then we can call that is a dynamic system. What is a static system? The time is constant there, so there will be no change in particles or with respect to time. Okay, then that we call as a static system. So we know that almost all the things in this world is like a dynamic system, because we know that even though we are not moving, there is a system is moving around us. So we will be talking that is with respect to that time frame. Okay, so in a static system, we can say that it is independent of time. Okay. For a dynamical system, the equation of motion do not contain a time explicitly. Okay. So we can say that for a dynamical system, for a dynamical system, the equation of motion do not contain time t explicitly. What it means is that we don't need to represent that there is a time involved. Okay, so in a dynamical system it is clear that it is moving with respect to time, so we don't need to express that always there is a representation in terms of time. Okay, so that what I means is that is simply if I can say that dx by dt. Okay, let me have x is there, and dx by dt is what I can just simply represent as y. Now we can say that y is what? It is dx by dt. And next I can represent y dot. Y dot is what? It is d square x by dt square. Okay. So if I just now if I represent y, then what it means? This is the change in x with respect to time. Okay. So I don't want to specify all the time is that y is equal to what? Y is equal to dx by dt. Y dot is equal to dx by dt. It is clear from that definition is that y is dependent on a time frame in that case. Okay. So that is the main idea of that, and we used to call that the equation of motion do not contain a time t explicitly. In such system we call as autonomous system. Autonomous systems. And an example of that, in such case the equation of motion will be like this: d square x by dt square plus f x dot plus f of x is equal to 0. Here you can see that what is f of x dot means, that is dx by dt. Okay, why f of x dot is I have represented, because I have represented it because there will be two cases here. What is f of x dot means? What is x dot? X dot is dx by dt. So what is f of x dot means? F of x dot is any function. It is any function of velocity, right? So it is any function of velocity where x dot is equal to dx by dt. So the second term will be any function of velocity with respect to the one, and the first one f of x is what? It is any function of with respect to the displacement. Okay, so then we have f of x is what? It is a function of velocity, as we have said. It is function of displacement x. Okay, x dot. Okay, now in that representation, let me make it a bit more clear. That is, let me just take the example of this equation. So I can represent this equation as y is equal to what? I have introduced that x dot. Y is equal to x dot, and where dx by dt is equal to x dot, that is equal to y, right? Okay, and this equation, if I just represent this equation as equation number 1, then equation number 1 becomes, in that case, equation number 1 becomes, how do we represent, that is, this is what, this will be dx dot. Okay, this I can just represent that y is equal to x dot. So here we have x is there, y is equal to x dot, dx by dt is equal to x dot, and is equal to y, right? And I can represent that d square x by dt square, which is what, which I can represent in terms of what, it will be dx dot by dt, right? It is dx dot by dt. Dx dot means dx by dt. So which I can represent as dy by dt. Clear? What I have done, hope you are clear with the discussion. So I have just represented dx by dt in terms of x dot, then we have replaced it with y, and d square x by dt square what? That is dx dot by dt, which is equal to dy by dt. Now this equation becomes what? It becomes dy by dt plus f of y plus f of x is equal to 0. And this is our equation, or rather this equation I can also represent that dy by dt is equal to what? Minus f of y minus f of x. Okay, or this can be plus, let me keep it a bracket over here, and this is our equation number 2. Okay, dy by dt minus f of y plus f of x in the bracket. Okay, so y is what? It is fx dot. So we have two equation now, we have represented in this fashion, and let me so this is our representation now. And if I need to find the solution of this one, or rather I could say that for a general solution, in order to derive a general solution of this equation, so I am giving few more substitution, that is dx by dt. Okay, dx by dt is equal to p of xy. So that is equation number 3, and we do represent that dy by dt equal to q of xy, because now we know that dx by dt has a dependency of p and xy, sorry, x and y, and we have dy by dt has a dependence on x and y over here. So then we'll substitute dx by dt equal to p of xy, dy by dt equal to q of xy, where p and q is a function of x and y. Okay, p and q are function of x and y. Okay, now here we need to represent few representation. That is one representation I would like to say that what is dx by dt? Dx by dt is a function of a xy, I already said. So what we will be getting? If there is a x and y, two coordinate is there, then what we are going to get? We will be getting a plane. A plane means that there is a y over one direction where we will be having x over that another direction. Okay, right? So we can represent that as a simple plane over there where we have two coordinate system x and y. Okay. Now in with that idea, I'll be introducing a term which is called phase plane. Why we are doing this whole thing is that how do we solve a nonlinear differential equation? For that we are deriving certain quantities and terms we are representing. So first term I am introducing is that is phase plane. Okay, so in a phase plane, what is a phase plane is that the quantities, okay, the quantities x and y we are having, right? Y can be considered as a, as I said, consider as a Cartesian coordinate in xy plane. Okay, simply you can just represent that is a as a linear case. This is x and this is y. So this is what, this is a plane, right? If you can, the quantities x and y can be considered as a Cartesian coordinates in xy plane, and that plane we used to call as, that plane is called as phase plane. It's very simple. If you can represent dx by dt and dy by dt as a simple plane, I already said that what is a dx by dt is. Dx by dt is a very small area. A small area means what? It has a breadth and it has a width. Okay, it has a height and it has a width or other. So this is our y and this is our x. So when you are just describing, you are getting actually an area. Okay, so p of xy is giving a phase plane corresponding to that where x and y, where p is a function of x and y. So if you just give a this one, you will be getting an area corresponding to that. And now what do I say is that we got an area right here. So we got a area or a phase plane corresponding to that where x and y we consider as a Cartesian coordinate. Now the next term I will be like to introduce is that phase trajectory. What is phase trajectory means? It is simply if I said if x is varying and y is also varying with respect to that, and correspondingly if there is a motion corresponding to that, this is a representation of a trajectory or a curve corresponding to that with respect to the change in x. Okay, so what is phase trajectory is that, so we have two equation, equation number 3 and equation number 4. So we can just dividing equation number 3 and 4. So what we basically will be getting is that dy by dx, okay, or 4 by 3. Okay, dividing 3 by 4, we'll be getting dy by dt divided by dx by dt. What is dy by dx is, that is dy by dt divided by dx by dt. Dx by dt. So let me make it as this is 4 by 3, then it is more clear. Okay, dividing 4 and 3. So we will have dy by dx is equal to dy by dt dx by dt. So which is equal to what? That is what we are basically gonna get. What is dy by dt is? Dy by dt, we know that it is f of y plus f of x. We already have represented, that is in dy by dt is equal to minus f of y plus f of x, like we represented, right? So let we, if you doesn't consider minus, we can say that it is dy by dt is equal to f of y plus f of x, right? So that you can substitute here. And what is dx by dt? Dx by dt is what? It is y. Okay, it is y, because y is equal to what? It is dx by dt, or rather x dot. Okay, so we can represent that is f of y plus f of x is equal to y. And simply, or rather we can just simply represent this as dy by dx is equal to what? It is q of xy divided by p of xy. Okay, and if I just give this equation as equation number 5, what equation 5 describes? Equation 5 describes is what? Equation 5 is correspond to a what? Correspond to a definite trajectory or a definite curve. So we'll be observing a curve corresponding to that in the phase plane. In the phase plane, which we known as, which is known as phase trajectory or phase curve. It's that simple, nothing very complicated, because we need to address a nonlinear equation first. In that nonlinear equation, with respect to that, if you just take f of y plus f of x divided by y, then you'll be getting the corresponding dy by dx. And what is dy by dx is? It is actually, you'll be giving a phase curve corresponding to that. Okay, so phase trajectory you'll be getting, and phase or phase trajectory or phase curve will be corresponding, you will be getting, because you can understand that is from the curve itself. So if there is a variation with respect to x, there will be a trajectory corresponding to that, you can trace out, so which is called phase trajectory. It will be very simple, but it is very important to understand. And next I will be move on to the case of now what we do is that next we are trying to integrate. Next we are trying to integrate. If you integrating equation 3 and equation 4, and what we will be getting is that in that time we will be getting what? X is equal to x of t you will be getting, right? And similarly you will be getting also y is equal to y of t. So you have a representation of x and y in terms of time dependence. Okay, x of t or y equal to y of t you will be getting. And this equation, this is a, we call as a parametric equation. Okay, this parametric equation we call as parametric equation of the trajectory. Okay, so when you integrate equation number 3 and 4, what is 3? Dx by dt equal to q of xy, sorry, p of xy. And equation number 4 was dy by dt is equal to q of xy. Then you do integration, what you are going to get is x is equal to x of t and y is equal to y of t. That is, you will be getting a parametric equation of the trajectory corresponding to that. Okay, now let me just give an example of a two important representation, that is about singular point. Singular point. And what is singular point is that a singular point is a point in xy plane. So it is a point in x0 y0 of a phase plane. Okay, so when you consider a phase plane, so singular point is a point where P of x0 y0. So at the position P of x0 y0 will be equal to Q of x0 equal to 0. If there is a point in phase plane, that is at, if you, for example, a point x0 y0, consider a point in x0 y0 in our xy plane. Okay, in that plane P of x0 y0 and Q of x0 y0 equal to 0. Okay, we already said what is Q of x0 y0, and or for clarity let me make it as dx by dt is equal to x0 y0 equal to dy by dt at x0 y0 is equal to 0. Then we can say that there is a singular point is there. So that point we used to call as singular point. Okay, so the point at which dx by dt at x0 y0 equal to dy by dt at x0 y0 equal to 0. When we consider x0 and y0 as a 2 point or a point in a phase plane. Okay, so some coordinate, for example, let me mark an example. If I just mark an example here, and this is x0 and y0, and at this point if p of x0 y0 equal to q of x0 y0 equal to 0, then this point we used to call as the singular point corresponding to that phase plane. And similarly we have another discussion is that is about ordinary point. Okay, what is ordinary point is that an ordinary point is, for example, if in this case what is a scenario at this point p of x0 y0 equal to q of x0 y0, what it means is that at this point p of xy and q of xy is vanishing, right? If both are vanishing at this point. Okay, what is ordinary point is that if there is a point p of x0 y0 and q of x0 y0 do not vanish simultaneously. What it means, if you find an example of any point, okay, if you consider any point, in that point q of x0 y0 can be 0, but p of x0 y0 will be not equal to 0. Such point we used to call as ordinary point. So what it means is that p of x0 y0 and q of x0 y0 do not vanish simultaneously. That is a point we used to call as ordinary point, and we also see in the case for a both vanishing case which is called singular point. Okay, so saying one more point, I will wind up today's session, that is about representative points. Okay, it's about representative points. Representative points. Okay, so what is representative points is that the derivative of 3 and 4. Okay, the derivatives 3 and 4 dx by dt are x and y component of velocity at a point in phase plane, right? So when you consider a phase plane xy, so we have the derivatives from equation. So we have few derivatives from equation 3 and 4, that is what dx by dt and dy by dt. Okay, and what is basically represent dx by dt and dy by dt. Okay, so first one is representing the position, and this is representing the velocity component, right? Velocity component, and this is also a velocity component representation, or rather we can say an acceleration component. Okay, also we have treated this as a velocity component itself. Okay, so this is basically representing x and y components of a velocity at a point x in plane. Okay, x and y component component of velocity in phase plane, right? So these are two other points. And what do we this represent? Okay, so dx by dt and dy by dt basically representing the x and y component of a velocity in a phase plane, and this is we call as representative points. Okay, representative points. And for to more to be clear, so I can represent this equation as like this. This you can consider as a velocity components, that is vx is equal to dx by dt, that is equal to what? P of xy. Okay, and the second one is py is equal to dy by dt, which is equal to q of xy, where vx and vy are the two components of velocity. Then if you can represent dx by dt and dy by dt as a xy component of velocity in phase plane, and these two we call as representative points corresponding to a particle. So this is a general representation of a motion in a nonlinear system. Okay, so how do we describe a motion in nonlinear motion? We have just described with a few example and few terms. That is, one is phase plane, phase trajectory, then parametric equation of trajectory, singular point, ordinary point, and at last we have said about representative points, that is a xy component of velocity in a phase plane representation. Now what we need to do is to elaborate or to understand this phase trajectory of a linear system and a non-linear system. We need to take into consideration. For that, what we will do is that, so we need to identify the phase trajectory of a, how the phase trajectory of a linear system we need to examine. Okay, and also we need to examine the phase trajectory of a non-linear system. Okay, phase trajectory of a linear system and a non-linear system we need to expand or explain. So for that we'll do, for a linear system we'll consider a harmonic oscillator, and for a non-linear discussion we'll consider a damped harmonic oscillator. Okay, so by taking those two example, you can actually find out the different example of the singular point and the phase trajectory and the corresponding representation of what. Okay, so by taking the example of harmonic oscillator, damped harmonic oscillator, we can understand how do we represent a phase trajectory, how do we identify the singular point, how do we identify the ordinary point, and what is a representation point corresponding to an harmonic oscillator and a damped harmonic oscillator. Okay, that part of the discussion will keep to next lecture. So with that discussion about the different general aspect and introduction part of the nonlinear equations, we'll wind up today's session. You can just very simply